Do you have a that radar love?
There you go. There you go. That one. Hey. Hello. How are you?
Does this control it? It does.
So
Point it that way.
The
Electric, yeah.
And then
there's an electric pointer in the middle.
We're just doing a nominal concentration.
There you go. All right, I think we are ready to begin with our next talk. So, Dr. Webby, would you like to introduce your students?
Yeah, this is
Sure.
Erin Whetzel is a senior in chemistry in our School of Science, and she's a double major.
Yes.
Right, chemistry and biology. She's a really honor student and one of our very best. She's at the very top, and she's prospecting to various places. So our talk today is on bioremediation of lead with solid tea waste. You know, Erin and 3 other students were in my quant lab, quantitative analysis. Was that in the fall?
Yeah.
And they got done with the lab, I think about 3 weeks earlier. And so I asked them, what are your plans? What are you going to be doing for the remaining 3 weeks of, you know? And they said, we don't know. I said, don't tell me that because I can get you busy. And they say, doing what? I say, you know, research, and Michaela is one of them, and they say, oh yeah. So I really got these 4 students just started, and so this has probably been what, 6 weeks, 8 weeks since they've been doing this, and everybody has a medal they are working with, and so we have 5 medals and 4 students, and she's presenting here on lead, and the others are going to present. 2 of them are presenting down in Mobile.
All right, so like you said, I'm doing bioremediation of lead with solid tea waste. And I'm Erin, Whetzel, in case you didn't catch that. Okay, so we all know lead is bad, and it contaminates our environment from industrial waste to old paint, old plumbing. It leaches into our environment, our soils, our water, could even get into our drinking water. And that's very bad because it's toxic to us, it's toxic to the environment, it's toxic to plant and animals. If you get it in streams and lakes, then it can accumulate in fishes and game. So if you want to go hunting or fishing, then your food will be contaminated with lead. So we have to find a way to clean this up. So there's a couple different methods. A lot of big industrial cleanup focuses on neutralization, precipitation, and ion exchange. They don't work as well with smaller concentrations of lead, and a lot of them involve putting chemicals into the water, which then is not as environmentally friendly to have to add chemicals to your water, because then not all of it can be removed. Usually they're less toxic than what you're trying to remove, but it's still better to find other ways, which is why we're focusing on adsorption, which is adding some kind of solid. A lot of times it's a organic, biological kind of solid that you add to the water, and it will adsorb to the ions, to the metals, so the metals will come out of solution. And in this case, we're using tea, so it'll stick to the tea and then get out of the solution. So then we can remove the tea, and that removes the metal with it. So we're looking at tea because tea, solid tea waste, we're not talking about the tea you buy from the store and then use. We're talking about if a restaurant brews the tea and then that solid that's left over, they'll just throw out. So it's really readily available and very cheap because it's waste, it's trash that we're throwing away. And it's everywhere. You know, there's sweet tea everywhere in the South. There's tea, unsweet tea in the North. There's tea in lots of other cultures that they'll just throw this out. So, I know Dr. Mwebi's done a little bit of work before with this, and they found it absorbed to copper and a couple other things. And there's some evidence in the literature that it would make a good adsorbent. Okay, so the objectives of the study is to investigate the ability of the solid tea to adsorb lead, to see if it's good at it at all, to determine the amount of lead it can take out of contamination, take out of solution, to see how much it can take out, to determine the effect of particle size, which is how big the tea particles are, to see if that makes any difference at all on how well it adsorbs the lead, and to determine the mechanism of adsorption, to see how it adsorbs the lead. Okay, so the first thing we did was we brewed our tea. We brewed it ourselves to make sure it was controlled and we knew exactly how the tea waste had come to be. So we bought Lipton tea from the store, just from your local grocery store. We brewed it at 90 degrees Celsius, or we started at 90 degrees Celsius, about that, for about 5 minutes. And then after that, we took the solid out and we spread it on glass pans, stuck it in 50 degrees Celsius ovens, and dried it until there is no longer moisture in it. After we dried it, then we sifted it. We just used these big metal pans with basically grates that were measured for a certain particle size. So we separated it by size into 30 microns, 300 microns, 425 microns, and 600 microns. Okay, so after that, then we measured out 2.5 grams per sample. We took a bunch of different samples, did it by size, and then we did 100 milliliters of 100 parts per million lead in each one. And each sample went into an Erlenmeyer flask and got put on this, on what we call shakers, which are these big, like, square thing that you have holders on that you put the flasks in, and it just kind of like rotates it and shakes it automatically, so you don't have to sit there and do it. But we shook them overnight, and then we would separate the liquid from the solid, which the liquid would be the filtrate, and the solid would be the residue. And so the residue we ended up freezing, and we freeze-dried it so it was dry and could be stored, wouldn't mold. And then the filtrate, the liquid part, we kept for analysis to see if there was any lead left in the liquid. Okay. So after that, we took the filtrate, the liquid part, to analysis, which we use atomic absorption analysis, which is a way to use, it uses a flame and it sprays the sample into the flame, and then based on the characteristics of the flame, then you can tell if any of the lead is in that sample or not. So we use this to find the concentration of lead left in our sample. So after all of this happened, then we did not detect any lead at all in the filtrate. So there was no lead left in the liquid part of our sample, which means that, well, the lead has to still be somewhere, so obviously it should still be in the residue, the solid part that we freeze-dried and put away. This is a good news. I know it's negative results, but it's good news because that means the lead actually did absorb to the tea, and the tea did what we hoped it would do. Okay, so after this, then we started a sequential extraction method on the residue that we had saved before. So we got that back out and took, I think there's only 1 gram of it that we were able to save. And we took it in, it says 4 fractions, but it's actually 4 separate steps. Do the acetic acid. It's kind of the same way we did it before, except instead of adding lead solution, you take the solid that we already have, you add acetic acid to it, shake it overnight, separate the liquid from the solid, keep the liquid for analysis, and then dry the solid again and put it on the next fraction, which is hydroxyl ammonium chloride. So we did that again for another, shake it overnight again, separate it again, take the solid, add some hydrogen peroxide to it, do that all over again, and in the very last fraction we use concentrated acid, which we use nitric acid and hydrochloric acid in very concentrated amounts. And that would be our residual fraction, which is where we're trying to digest the tea and make sure all of the lead got removed from it. So we can see, even if it didn't get taken out of the other parts, we know that the lead's there. And in between each fraction, then the tea was washed with a little bit of water, just to make sure none of the chemicals from the previous step were in the next step. Okay, it's kind of a picture diagram of what we did. So the first part there, shaking with lead, was the initial putting, like it's the loading stage. That was when we put the lead on the tea. We took the dried tea and then put the lead solution in it. And then the arrow down represents the, arrow there, represents the solid residue getting put into the next fraction. And so after shaking with each one, then we take the solid out, put it to the next one, and we have the filtrate that we keep for analysis later. And all the way down to the strong acid. And at this point, we should have seen no more solid left, like it should all be dissolved, but we ended up with a little bit, and that solid just kind of got kept for later, just in case. But the majority of it was filtrated by then and got used for analysis. So our results, kind of interesting for lead. Lead was not seen in any of the fractions except for the final residual one, which means that each of the fractions kind of represent a different way the tea interacts with the lead. So the original one we already talked about, that was just to see if the lead was absorbed to the tea. And the fact that we saw no lead in our filtrate means that the tea was absorbed, the lead did absorb to the tea. Acetic acid kind of represents our loosely bound, kind of easily removed lead. So if the tea had not been very strong and it had just kind of associated with the lead a little bit, the acetic acid should have knocked it off. We saw that there is no lead after an acetic acid fraction, which means that the lead is not loosely bound. Process of elimination should mean it's tightly bound. Hydroxyl ammonium chloride is, which one? Get these two mixed up. Hydroxyl ammonium chloride, oh, that's the reducible one, which is if it was in reducible, if it was in a reducible part of the lead, of the T, then it would get knocked off here, and that's kind of more tightly bound. Hydrogen peroxide is kind of the opposite, is in oxidizable parts or organic parts. And we saw it did not get knocked off on either of those two, so it was very, very tightly bound because we did not see any lead come out of the T until final digestion with the concentrated acid. Here you can kind of see about particle size. We didn't see any correlation between particle size and how well it absorbed lead. You know, we separated into 3 different sizes, 300 micron, 425, and 600. And they all, this is the data from the final fraction, the residual one. But the data was pretty much all the same throughout. So no effective particle size. Doesn't matter if you separate it out. And this is actually kind of interesting because, well, I told you before, we didn't see any lead coming out any of the fractions except for the residual one. But even the residual one only showed about 12% of the lead that we originally put in. So trying to figure out where the rest of the lead went. Now, a lot of it, maybe about half, kind of gets lost through the analysis because every time you take a solid out and you separate the solid and the liquid, then some of that solid gets still stuck in the liquid phase or gets kind of thrown out. It's lost in some ways. But still, we did not expect this little of the lead in there, which we think is because it was not digested all the way. Typically you use hydrofluoric acid, which is really nasty stuff, so we did not use hydrofluoric acid. For really complete digestion, we would have to get a hold of that. But because we did not use hydrofluoric acid, then we think that it was not completely digested, so there could still be lead left in that solid T even after all of the digestion. But the main point and takeaway is that the T definitely firmly held this lead and did a very good job absorbing to it. So yeah, solid T has very high potential for this. We were not able to quantify the maximum amount, but we did quantify, well, what we saw was that 468 milligrams of lead per 1 kilogram of T was absorbed. But it had the potential to do 4,000 because that's what 4,000 milligrams of lead per kilogram of T is what we put in to solution, and the 468 is what we saw coming out in that residual fraction. So 468 is kind of a confirmed amount, but 4,000 is what we think it did absorb. And it was strongly held because we didn't see it to the residual. Yeah, so we can continue with this work in a lot of different directions. There's a way we can quantify the maximum amount of absorption of lead. We actually do this with like a column kind of analysis, and you just keep putting lead through until until you finally see lead coming out, and then based on how much liquid you put through, you can see how much lead the T can absorb. So there's another kind of analysis we can do to quantify that. And we can also look at effects of things like pH, how concentrated the lead solution is, how much time we let it shake, or if there's any other metal ions, and other different factors that might affect how it absorbs. And we can also look at other heavy metals, which some of my other fellow students are looking at. And thank you, Jacksonville State University, and the Physical Earth Science Department for all of the support and help, and Dr. Webby. Yeah. And Michaela here and Cody are also been my fellows that have done other heavy metals, and we've been working together. So thank you.